Hello, welcome. First, we're going to be starting on the whiteboard today so we can make everything a whole lot easier. We're finally recording my voice, so thank you to that. And now we can get started on homework 2B. We are going to be using a PID controller and step functions to control the height of two different tanks. And what a PID controller is proportionality concept for K, and it uses the set point difference from what were our value given with some different inputs to figure out data for us. So what I'm writing right now is our PID controller equation. And we're going to take this equation from the form I have it in now and put it into a Laplace transform so it can be used as a step function. So when we do the Laplace transform, it takes it from K to Kc times E plus 1 over tau I of E over S, because 1 over S is the Laplace transform for an integral, plus tau over D of E times S. And now if we want to simplify this even more, we get Kc, and we take the E out, and then we want to put this all under one denominator, because the transfer function is always consistent upon a numerator and denominator, and the feedback loop is always consistent upon the top and the bottom. And I'll show you that later, but for right now, we're going to put tau I, tau D, and we want to keep our Laplace transform orders in descending, so our biggest up front plus tau I S, and then plus 1 all over tau I S. And the reason why we want to keep that consistent is so that when we go from a Laplace transform to a polynomial to a transfer function to a polynomial, we'll be able to know which is which. Um, so now that we have our PID is going to go into the system such as this. I'll show you what a feedback loops look like. So for our E, don't forget that E is equal to our set point minus our outlet, H2. And here's our set point, and here's our controller right here. And that is going to be monitored by our measuring device, GM. All right. And then here's going to be our process, what we call our process. But for right now, we're going to have GC, and that's going to be where this comes into play. And then we're going to have our GP. Simple process, but as you know, nothing is simple in chemical engineering. So what we have here is our transfer function is going to go here. And for our process, I'm going to explain that out real quick. So our GP is going to be equal to our given was R1 over A1, R1, S plus 1, then goes to 1 over R1, and then it goes to R2 of A2, R2, S plus 1, which then goes to H2, which then goes to our controller right here. And then when we take down this process, because it was given to us right here, Q2 equals 1 over R1 QC. So QC, this is cancel. But I'm going to take this function right here, if you can see, and I'm going to show you how HSP is equal to H2 plus H2, yeah. And then that makes H2 equal to HSP minus h2 gm. And then don't forget that this is all going through our feedback loop. So we have GC, GP, and we're looking for our H2. So we want to get H2 by itself. Do that, we multiply the GC, GP throughout, and we get H2 of 1 plus GC, GM, GP is equal to HSP of GC, GP. And then H2 then becomes equal to all over 1 plus GC, GM, and GP. Now, as I already said earlier, a transfer function has a numerator and a denominator, but as well a feedback loop has a top and a bottom. And as we can see, the GC and the GP is our top process. And so that is our top transfer function. And a transfer function has a numerator and denominator. So that means our top, our forward transfer function going forward equals to our top. And our denominator for our famward transfer function at the top is GCGP. And then that is going to be equal to 1 plus NF over DF times the GM portion, which is the numerator and denominator for the backwards portion. And then that means that we have H2 equal to HSP of and then that turns it into NF dB over DF dB plus NF. I think that explains everything. So now I'm going to take this and we're going to put this into Python code. So make it so that you're able to see more of me. Do right here. Do right here. This. Right there. Right. And if we can see everything, now we can start coding in Python. I have a chair. I actually was in a car accident. So now let's start. Define transfer function to polynomial as TF. And that's going to return P of TF dot numerator. And remember how I said we want that transfer function to be written correctly? That is why we're writing it with this -1. And then P TF dot denominator. transfer function, numerator, comma denominator. Look like RETURN as and then we want to be able to multiply transfer functions, so define TF need to input two different transfer functions, and we're going to multiply those numerators times the denominators to give us each that is needed. And then that is going to return it's a transfer function. So that should return a polynomial to transfer function as n1 times n2 times d1 times d2. Yep. And next, we want to define our feedback loop. TF underscore forward, TF underscore backwards. That's going to be NF denominator forward. And that's going to be equal to TF poly of transfer function underscore 1. It's going to be equal to ND poly b equal to TF poly underscore TF underscore b. Sorry, TN poly TF of what do we find? Numerator forward times denominator backwards. So numerator forward times denominator backwards. The comma is going to dignify that fraction bar. And then we have denominator backwards times denominator forwards plus numerator forwards times numerator backwards. And then last but not least, we want to define our PID system. So that has a proportionality constant and then two other constants, I and tau d. And then what we did for this is our transfer function for our PID, and the equation for that is written up here. And since we have it in descending order, and that is the way we input it, we want to put our S squared value in first. That would be KC times TAUI times TAUD, comma. So our next value is going to be KC times TAUI, comma, and then 1, so just times KC. And then we have TAUI, dot. All right, so now that we have everything defined, and we're able to do that, show and explain the block diagram. I did that. Describing. All right, so what we can start doing now is understand how we go from GC to GP, and that is going to be by we go that from QC to Q2, and that's going to be equal to transfer function of, well, we haven't put those variables in yet. So A1 is equal to 1, A2 is equal to 1, R1 is equal to 2, R2 is equal to 2, AC is equal to 2, TAUI is equal to 2.8, TAUD is equal to 0. Check enter. QC transfer function of QC to Q2. It's 1, comma, and then the denominator is A1 times R1 And then the s plus 1 just gives us 1 right here. We enter, and then q2 to h2 is going to be equal to transfer function of r2 enter, and then we need that full function for the process, and that's going to be qc to h2 is going to be equal to function multiplied of the two different transfer functions, so qc to q2, comma, and then q2 to h2. Okay, and now that we have that, we need to, so we have our process for the transfer function, but we don't have our top process. So we need to multiply our GC times our GP. And that is going to be equal to our forward process of the feedback. So transfer function underscore forward is equal to TF MULT of PID consisting of shift KC, comma TAUI, comma TAUD, which is then going to be multiplied by QC to H2, which is a subset of sorts. All right. And then our transfer function forward needs to go into our transfer function feedback. So TF underscore FB equal to TF underscore BACK. And that's going to be consistent upon our forward and our transfer function for going backwards, which is going to have a numerator and denominator. Transfer function feedback is equal to transfer function feedback. For our feedback, which is right here, need to forward and backwards. So transfer function underscore feedback would equal TF underscore forward, comma, TF underscore 1 is not defined. TF underscore FWD. All right, so define TF mode as TF1 comma TF2, N1 comma D1 equals okay, TF2 N2 comma D2 equals TF2 poly Okay, okay, okay. The -1s, all right. So NF comma DF equals transfer function to polynomial. Name TF underscore 1 is not defined. It's not. TF underscore F. All right, and now that we have our TF underscore FB, it's our feedback loop. We want to plot that. So T plot is numpy.polynomial.Polynomial from 0 to 100, 500. And then we're going to need T plot comma 2 is going to be equal to TF underscore FB dot step function for T equals T plot there. And then okay, so write and explain Python code. Derive the servo transfer function in terms of numerator and denominator polynomials before and backward rotation. Two things to the QC is the flow set by the controller. H choose local level second tank. Determine the transfer function. Okay. Simulate the step response to the transfer function in 2A. And then simulate the response to the forward function to consider. All right. So we do that. Equals sig dot L sum of transfer function going forward, comma T, so. And as you see, the line stays just in between the blues, which is what we want to see. Um, There you go. Have a good day.